Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
Great to be here.
Today, we are exploring listening to the cosmos, the next generation of gravity hunters.
And it's a huge topic. I mean, we're talking about machines that are almost beyond imagination, really. The most sensitive things humans have ever tried to build.
You know, I was thinking about this last night. I was just sitting outside looking up at the sky, and it really struck me that for what all of human history, astronomy has been visual. It's about looking.
Yeah.
We used our eyes, then we built telescopes, which are just better eyes, then radio telescopes to see, invisible light. But it's always been about photons, about light hitting a sensor.
That's been the entire foundation of astrophysics for centuries. The electromagnetic spectrum, from gamma rays all the way down to radio waves, it's all just light.
But we're at this turning point now. And I think it's as big as the invention of the telescope. We're finally learning how to move from just watching the cosmic movie to actually hearing the soundtrack.
That's a great metaphor. And it's a really popular one. But you know me, I have to jump in with a little scientific asterisk right away.
I was waiting for it.
Well, when we say listening, we need to be really clear. It's not sound. You know that old movie tagline?
In space, no one can hear you scream.
Exactly. And it's true. Space is a vacuum. Sound needs a medium, like air or water, to propagate. These things we're talking about are different.
So I'm not going to hear a whoosh if a black hole flies past me.
You'll hear nothing at all, right up until the tidal forces spaghettify you. But what we're actually detecting, these gravitational waves, they're not sound. They are, and this is the mind-bending part, they're ripples in the very fabric of space-time itself.
Space-time. Okay, so we're talking Einstein.
We are deep in Einstein territory. But the reason that listening analogy works so well is that the frequencies of these ripples, the rate they wobble, often falls right into the range of human hearing.
Oh, really?
Yeah. Between, say, 20 hertz and a few thousand hertz. So if you take the data from the detector and just pipe it into a speaker, you can literally hear it.
And we did hear it.
Oh.
About a decade back, right? The famous chirp.
The chirp heard around the world, a true game changer. But today, I don't think we should just look back at that first discovery. That was incredible, but that was generation 1, generation 2.
Right.
Today, we're looking forward because engineers right now are designing and prototyping machines that are going to make those first detectors look like antique toys.
This is the third generation. The Einstein telescope in Europe, the Cosmic Explorer in the U.S., and we're going to get into the really deep, nitty-gritty details of this prototype called E-Test. I was reading the design reports on that, and it's trying to do things that just sound impossible, like cooling a 100-kilogram mirror to near absolute zero without actually touching it.
It is engineering right on the bleeding edge of what physics allows.
Okay, so before we start digging these massive underground tunnels or building 40-kilometer-long tubes, let's back up. For me, for everyone listening, what is a gravitational wave? Assume I know nothing, except that Einstein had wild hair.
I know. Okay, let's strip it back. For a long time, we had Newton's idea of gravity.
The apple falling on the head.
Right. And he saw it as a force, an invisible rope connecting the sun to the earth, pulling it, action at a distance happening instantly.
That makes intuitive sense.
It does. But Einstein came along in 1915 with his General Theory of Relativity and said, nope, that's not it. He said gravity isn't a force at all. It's a consequence of the shape of the universe. It's curvature.
This is the mattress analogy, isn't it?
The mattress or trampoline analogy is still the best one we have. So picture a huge, taut rubber sheet. That's our space-time. Now, you place a bowling ball in the middle, what happens?
It creates a dip. A big well in the sheet.
Exactly. The bowling ball, our sun, is warping the space-time around it. Now, if you roll a little marble, the Earth past that bowling ball, it doesn't travel in a straight line anymore, does it?
No, it gets caught in the curve and starts to orbit.
It follows the curve, not because of a rope, but because the very ground it's rolling on is bent. That is gravity.
Okay, got it. Curved space. So where do the waves come from?
Well, now imagine you take away that single bowling ball and replace it with two of them, and they're spinning around each other at incredible speeds. They're not just sitting there creating a static dip. They're violently churning up the rubber sheet.
They're making ripples.
They are making ripples that spread out across the entire sheet, just like when you drop a stone into a still pond. Those ripples are gravitational waves.
So what kind of event in the universe is like two bowling balls spinning around each other?
That's the key. The analogy breaks down a bit with the stiffness. Space-time is unbelievably stiff. It's billions of times stiffer than steel. So to make a ripple that we can even hope to detect, you need an event of truly catastrophic violence.
Not just any old star.
No, you need something like 2 black holes, each maybe 30 times the mass of our sun, spiraling into each other and crashing at half the speed of light.
Half the speed of light. Wow.
That's the kind of event it takes to make a wave we can hear. And even then, by the time that wave has traveled for 1 billion light years to reach us here on Earth, it's almost gone.
Yeah, I saw the numbers you sent over and I was sure it was a typo.
No typo, I'm afraid.
It said that the wave stretches and squeezes everything it passes through by less than the width of a single proton.
That's correct. Often it's just a tiny fraction of the width of a proton.
Okay, wait.
Yeah.
A proton is it's the tiny nucleus of a single atom. It's unimaginably small. How on earth do you build a ruler that can measure a change in distance smaller than the smallest part of an atom? It just sounds impossible.
It does, doesn't it? And the answer is interferometry. That's the technology that LIGO and Virgo, the current detectors, use.
Okay, break that down for me.
Imagine a huge L shape. 2 perfectly straight, long vacuum tunnels that meet at a right angle. At the corner, you have a laser and a special mirror called a beam splitter.
So it splits the light.
Exactly. It shoots a laser, splits the beam in 2, and sends 1/2 of the light down one 4-kilometer arm and the other half down the other 4-kilometer arm.
So it's a race.
It's a perfect race. The light travels to a mirror at the far end of each arm, bounces back, and returns to the corner where it started. Now, if those 2 arms are exactly the same length, the 2 returning light waves meet up perfectly out of sync.
They cancel out.
They completely cancel each other out. It's called destructive interference.
Hmm.
The detector that's waiting for the light sees only darkness.
But then a gravitational wave passes through.
And that's the moment. The wave stretches one arm, and at the same time, it squeezes the other. So for a split second, one arm is a tiny bit longer, and the other is a tiny bit shorter.
So the race isn't a tie anymore.
It's no longer a tie. The light in the longer arm has to travel just a little bit farther. So when the 2 beams get back to the corner, they're not out of sync anymore. They don't perfectly cancel. A little bit of light leaks through to the detector.
And that flicker of light is the signal.
That flicker is the signal. That's the chirp of 2 black holes merging 1 billion years ago. But think about what we're measuring. It's a change in length of something like 10 to the minus 18 meters. It's like measuring the distance to our nearest star, Proxima Centauri, with an accuracy smaller than the width of one human hair.
It's still amazing to me that it works at all. But it does. I remember that moment in 2015. It really felt like a moon landing moment for science.
The GW150914. Absolutely. It changed everything. We went from thinking black hole mergers probably happened to knowing they did. We heard it. That signal, that rising whoop, was the sound of Einstein being proven right in the most extreme way possible.
And then, just 2 years later, in 2017, we got the neutron star merger. And that was different, wasn't it? Because that one we could actually see.
That was the birth certificate for what we call multi-messenger astronomy. Black holes are, well, black. They don't emit light. But neutron stars are made of matter, super dense matter. When those 2 smashed together, LIGO and Virgo heard the gravitational wave chirp.
And they could tell everyone where to look.
They sent out an alert to every telescope on Earth. And within hours, telescopes were swiveling to that patch of sky, and they saw it. They saw the gamma ray burst. They saw the kilonova explosion, the afterglow. We saw the gold and platinum being forged in that crash.
So we watched the movie and heard the soundtrack at the same time.
For the very first time. It was a revolution.
So if LIGO and Virgo are this amazing, and they clearly are, why are we even here? Why are we talking about spending billions to build something new? What's the problem with what we have?
There's nothing wrong with them. They're triumphs of engineering, but they've hit a fundamental limit. They've hit a wall. Or, maybe a better word is a floor, the noise floor.
This part of the research really surprised me. I always assumed the biggest challenge was just that these events are so far away. But a huge part of the problem is right here. The Earth itself is just too loud.
The Earth is deafeningly loud when you're trying to measure a wiggle the size of a proton. You have to fight a constant battle against noise. We usually break the enemies down into 3 main categories.
Okay, let's meet the enemies. Enemy number 1.
Seismic noise. Simply put, the ground is never, ever still.
You mean like earthquakes?
Earthquakes are the big ones, but it's much more than that. It's the ocean. Waves crashing on the coast of Portugal create a constant, low-frequency hum that travels through the entire European tectonic plate.
You're kidding.
Not at all. We call it the microseismic peak. Then there's us. Human noise. Cars on a highway 5 miles away, a freight train. Even just the wind pushing on the detector building is enough to shake the ground and mask a signal.
So below a certain frequency, it's all just rumbling.
Exactly. For the current detectors, that wall is at about 10 hertz. Below that, they are essentially deaf. The Earth is just shaking too much, and we're missing all the big, low-frequency events, the really massive black holes.
Okay. Enemy number 2.
Thermal noise. This comes from heat.
But the mirrors aren't, like, glowing hot, are they?
They're at room temperature. But to a physicist trying to do this measurement, room temperature is boiling hot. Temperature is just the random motion of atoms.
Ah.
The atoms inside the mirrors themselves, and especially in the super thin fibers that hold the mirrors, are constantly jiggling and vibrating because they have thermal energy.
And that jiggling of the mirror looks like a gravitational wave.
It creates a sort of a haze, a background hiss that limits our sensitivity, especially in the crucial middle frequency range.
Okay, so we have a shaking planet and jiggling mirrors. What's enemy number 3? This is the one that sounded like pure sci-fi to me. Quantum noise.
This is the deepest and most fundamental limit of all. It comes from the fact that light isn't a smooth, continuous wave. It's made of individual particles, photons.
Like rain on a tin roof.
That's the perfect analogy. It's not a steady shh. It's a random pitter-patter, pitter-patter. That randomness in the arrival time of photons at the detector creates a type of noise we call shot noise.
And this ties into the Heisenberg uncertainty principle.
Directly. Heisenberg's principle tells us there's a fundamental trade-off in nature. You can't know certain pairs of properties of a particle perfectly at the same time. For our laser light, those properties are its phase, which tells us about the timing and distance, and its amplitude, which is its brightness.
So if you measure one really well, the other gets fuzzy.
Nature itself forbids you from knowing both perfectly. This creates a sort of quantum fog that we have to peer through.
In the notes, I saw this term, squeezed light. It sounds like something from a cartoon. What is that?
It does sound funny, but it's an incredibly clever quantum trick that the detectors are actually using right now. Think of that quantum uncertainty as a fixed amount of air inside a balloon. You can't let any air out of the balloon. Heisenberg won't let you. The total volume of uncertainty is constant, but you can change the balloon's shape.
You can squeeze it.
You can squeeze it. If you squeeze the balloon around its middle, it gets really skinny in that direction.
Right.
But all that air has to go somewhere, so it bulges out at the ends.
So you're trading uncertainty. You make one measurement super precise, and in exchange, you make another one super messy.
That is exactly it. We design a system that squeezes the quantum balloon. We reduce the uncertainty in the phase of the light, which is what we use to measure the distance, and we dump all that extra uncertainty into the amplitude, or the brightness, which we don't care about as much.
So we are literally hacking the laws of quantum mechanics to hear black holes collide.
That is not an exaggeration. We are. But even with squeezing, there are limits. The current detectors, as amazing as they are fundamentally limited by their size and their location on the noisy surface of the Earth. To hear the very first stars, to hear the whisper of the Big Bang itself, we have to do something much, much more ambitious.
And that brings us to generation 3. And it seems like there are two competing philosophies here. You've got the Europeans with the Einstein telescope and the Americans with the Cosmic Explorer. Let's start in Europe with ET.
The Einstein telescope, or ET, is a complete reimagining of what a detector can be. The European consortium looked at that number one enemy, seismic noise, and they made a very bold decision.
If you can't beat it, run away from it.
Or in this case, dig. The entire Einstein telescope is planned to be built deep underground.
How deep?
200 to 300 meters down, about 1,000 feet.
What's it like down there? What's the advantage of being in a giant cave?
It is arguably the quietest place on Earth. Once you get that deep, you are shielded from almost all the surface noise. The wind, the cars, the ocean waves, it all gets filtered out by the hundreds of meters of solid rock above you. The rock itself is your vibration shield.
A scientific bunker.
A very, very large and sophisticated one. And it's not just the location that's different. The shape is too. LIGO is an L shape. ET is a triangle.
A triangle. Why? Is there some special physics in a triangle?
There's a special efficiency. An L shape is one detector. A triangle, with its 3 corners, lets you build 3 detectors inside the same tunnel system. You can bounce lasers between corner A and B, B and C and A.
So you get 3 detectors for the price of, well, one giant triangular tunnel.
Pretty much. And it also helps you solve a puzzle called polarization. Gravitational waves can wiggle space-time in different ways. They can stretch it along plus sign axes or along cross sign axes. A single L-shaped detector has a hard time telling the difference.
But the triangle can.
But the triangle, because its arms are at 60-degree angles, can triangulate the signal, so to speak. It can figure out the polarization all by itself, which tells you more about the physics of what you're looking at.
That's pretty clever. Now, I also read about this xylophone configuration, another musical term.
It is. This is the design's answer to the conflict between thermal noise and quantum noise. Remember, to beat quantum noise, that random pitter-patter of photons, you want a very powerful, very bright laser. More photons smooths out the randomness.
Like taking a picture in bright light instead of a dark room. Less grainy.
Perfect. But a high-power laser carries a lot of energy, and some of that energy gets absorbed by the mirrors and turns into heat. And what does heat create?
Thermal noise. The jiggling atoms.
Exactly. So you have this catch-22. To hear high-frequency signals, you need a powerful laser. But to hear low-frequency signals, you need things to be super cold, which means a low-power laser. You can't have it both ways.
So what do?
You build 2 detectors in one. That's the xylophone. In each 10-kilometer arm, there will be 2 parallel interferometers.
Like a woofer and a tweeter in a speaker system.
That is the perfect analogy. You'll have the high-frequency detector, the tweeter, which will use room temperature mirrors, and a super high-power laser to listen for the high-pitched sounds.
And the woofer.
The low-frequency detector. This one will use a low-power laser to keep things from heating up, and its mirrors will be cryogenically cooled.
How cold are we talking?
About 10 Kelvin. That's minus 263 degrees Celsius, just 10 degrees above absolute zero.
Okay, so that's the European vision. Dig a deep triangular hole and put a woofer and a tweeter inside it. What about the Americans? If ET is about going deep and cold, Cosmic Explorer sounds like it's just about going big.
The philosophy of Cosmic Explorer, or CE, is elegantly simple. Bigger is better.
How much bigger are we talking? LIGO's arms are 4 kilometers long.
CE is being designed with arms that are 40 kilometers long.
40, 10 times longer. Yeah. That's not a lab, that's a highway. How do you even build something that long and keep it straight? Doesn't the curvature of the Earth become a problem?
It absolutely does. Over 40 kilometers, the Earth curves away by about 125 meters.
So you can't just lay it flat on the ground?
No. You either have to build the ends up on giant earthen berms, or you have to dig a trench that's over 100 meters deep in the middle. It's a colossal civil engineering project. They're scouting for the flattest, most geologically stable places in the country, like the desert Southwest or the high plains.
But why? What is the payoff for that massive headache?
It's all about the signal. The amount of stretching a gravitational wave causes is relative. It's a strain. So if the wave stretches space by, say, 1 part in a trillion, a 1-meter stick gets longer by 1/trillionth of a meter. But a 40-kilometer arm gets longer by 40,000 times that amount.
So a longer arm just feels more of a stretch. The signal is literally bigger.
The signal is 10 times bigger just by making the arms 10 times longer. So instead of fighting to lower the noise floor, you're just turning up the volume of the universe's signal.
So it's 2 different paths to the same goal. ET is trying to build the quietest room in the world to listen.
And CE is trying to build the biggest ear.
And they're not really rivals, are they? They're meant to work together.
They're a global network. They complement each other perfectly. ET, being underground and cryogenic, will be the undisputed king of low frequencies. It will hear the mergers of giant primordial black holes. CE, with its huge arms, will be the master of high frequencies, hearing the fine details of what happens when a neutron star gets torn apart.
The woofer and tweeter for the whole planet.
Together, they'll cover the entire gravitational wave symphony.
Okay, this is amazing, but it's still kind of on paper. You can't just go and spend billions on a 40-kilometer tunnel without being sure the tech works. And that brings us to the prototype, the e-test facility.
This is where theory gets put to the test. This is where the silicon meets the vacuum chamber.
E-test. This is being built in that border region of Belgium, the Netherlands, and Germany.
That's right. And it's not a mini Einstein telescope. It's a very focused test bed. It's designed to solve what is arguably the single hardest technological challenge for the entire project: the cryogenic mirror and its suspension.
Let's talk about this mirror. In LIGO, the mirrors are made of glass, right? A special kind of glass.
Ultra-pure fused silica. It's fantastic at room temperature. But remember, for ET's low-frequency detector, the woofer, we have to go down to 10 Kelvin.
And you can't just freeze the glass mirror.
You can, But something bad happens to glass when it gets that cold. It's a property called mechanical loss. Think about a crystal wine glass. If you ping it, it rings for a long time, right? Dying.
Right.
That's low mechanical loss. It holds onto the vibrational energy. Fused silica, when you cool it way down, becomes the opposite. It becomes acoustically dead. If you could ping it, it would just go thud. It turns vibrations into heat very efficiently.
And that heat is thermal noise. So cold glass is noisy.
Very noisy, paradoxically. But there's another material, crystalline silicon. At room temperature, it's so-so.
Yeah.
But as you cool it down, it becomes almost acoustically perfect. It becomes one of the quietest materials we know of.
So you have to switch from glass to silicon. But silicon's opaque. It's what computer chips are made of. You can't shine a laser through it.
You can't shine a visible light laser through it. Our eyes see it as a shiny gray metal. But it turns out that silicon is transparent to certain wavelengths of infrared light.
So you have to change the laser too.
Everything has to change. The laser wavelength has to shift from LIGO's 264 nanometers out to 1550 or even 2000 nanometers, which means you need all new optical coatings, new sensors, new everything. And this mirror isn't small.
Big.
The one for e-test is about 100 kilograms, a massive, perfect cylinder of pure silicon.
Okay, this is the part that my brain just can't get around. You have this 100-kilo block of silicon. You have to hang it by a thread in a giant vacuum tank. And you have to cool it down to minus 263 Celsius. But you cannot touch it.
That is the challenge.
I mean, if I want to cool my coffee, I put it in the fridge. The cold air touches the mug.
Yeah.
That's convection. Or I can put an ice cube in it. That's conduction.
Right.
But in a vacuum, there's no air.
Yeah.
And you can't just clamp a cooling pipe to the mirror.
Yeah.
Because the refrigerator motor would vibrate and shake the whole thing.
The vibrations from a standard cryocooler are 1 billion times louder than a gravitational wave. Any physical contact is forbidden.
So how do you get the heat out?
You have to use the third form of heat transfer, radiation.
Letting it radiate away.
Exactly. Every object with a temperature glows in infrared. The hot mirror radiates its heat away as infrared light. So the engineers are building what they call a radiation shield, or a cold box, all the way around the mirror, but not touching it.
So a box inside the bigger vacuum tank.
A box with double walls. The outer wall is cooled with liquid nitrogen to about 80 Kelvin. The inner wall is cooled with liquid helium down to 4 Kelvin. And the inside surfaces of that inner wall are painted perfectly black.
Why black?
Because black surfaces are excellent at absorbing radiation. So the warm mirror hangs there in the middle. It sees these incredibly cold black walls all around it, and it radiates its heat energy towards them.
It's like when you stand next to a cold window in the winter. You feel cold, not because the cold is coming in, but because your body heat is radiating out to the cold glass.
That is precisely the effect. But there's a huge problem. It's a law of physics called the Stefan-Boltzmann law.
Sounds important.
It says that the amount of energy an object radiates away is proportional to its temperature to the 4th power.
To the power of 4, so it drops off really fast.
Incredibly fast. So when the mirror is at room temperature, it's radiating a lot of heat, and it cools down pretty quickly. But as it gets colder and colder, the amount of heat it radiates slows to a crawl. The last few degrees, from say 20 Kelvin down to 10, could take months.
Months. You can't wait months for your detector to turn on.
You can't. So the e-test team is planning a very delicate trick. Early in the cool down, they might intentionally let a tiny amount of ultra-pure helium gas into the chamber.
You break the vacuum on purpose.
Just for a little while. The few gas molecules will bounce back and forth between the warmer mirror and the cold shield, physically carrying heat away. It's like creating a tiny temporary breeze. Then, once the mirror is cold, you have to pump every last one of those gas molecules back out again.
That sounds risky. What if some of that gas freezes onto the mirror's surface?
That's the danger. A single layer of ice on that perfect surface would scatter the laser and ruin the experiment. It's an incredibly fine line to walk. And that's exactly why you build a prototype like e-test. You learn how to do the dance here so you don't fail on the main stage.
Okay, that's the cooling. What about holding it still? The design report talks about an inverted pendulum. A normal pendulum hangs down. What's an inverted one?
Think about balancing a broomstick on the palm of your hand.
Okay, it wants to fall over.
It's naturally unstable. But that instability is its strength. Because it's always on the verge of falling, it's incredibly isolated from horizontal motions of your hand. If you move your hand side to side, the top of the broomstick tends to just float in place because of its own inertia.
It decouples the motion.
Precisely. The e-test suspension will sit on a platform supported by 3 of these inverted pendulum legs. They are the first line of defense against horizontal seismic noise like an earthquake wave.
It's like a Hollywood Steadicam rigged for mirror.
A very, very expensive, very cold one. And from that platform hangs the next stage, the super attenuator.
Which is basically a chain of springs and weights.
A very long chain. Imagine hanging a weight from a spring, then hanging another spring and a weight from that, and so on for several stages.
Yeah.
Each stage acts as a filter. A shake at the top gets reduced by a factor of 100 by the time it reaches the bottom.
Like a slinky made of slinkies.
Exactly. And they use clever tricks like something called a geometric anti-spring to make the whole chain behave as if it's incredibly soft and long. The whole goal is to push the natural resonance frequency of the pendulum down to almost nothing.
What does that mean, the resonance frequency?
It's the frequency at which it naturally wants to swing. For the E-test pendulum, they're tuning it to about 30 millihertz. That's one swing every 33 seconds.
That's incredibly slow.
It's so slow that any normal vibration, a truck driving by at 50 hertz, an ocean wave at 1 hertz, is so much faster that it just can't shake the pendulum. It gets completely filtered out.
But I saw a specific detail in the report about a 13 hertz bounce mode. What's that?
Ah, yes, the vertical bounce. The mirror isn't just swinging, it's also hanging on fibers that act like tiny springs, so it can bounce up and down like a spider on a web.
A yo-yo?
A very, very tiny yo-yo, and you have to be so careful about the frequency of that bounce. If it happens to be right in the middle of the frequency band where you're trying to listen for gravitational waves, every time you hear a signal, the mirror itself will start to resonate and bounce uncontrollably.
The opera singer breaking the wine glass.
The exact same principle. It's a resonance disaster. So the engineers carefully designed the suspension so that the bounce mode is parked at around 13 hertz, which is just below the sweet spot where ET will be most sensitive. They're pushing all the bad vibrations into a frequency graveyard where they don't care about listening.
It really is like every single atom, every vibration, every source of heat has to be calculated and controlled.
And it all has to be controlled remotely, because once you seal that tank and start the months-long cool-down process, that's it. You can't go in with a wrench. It has to just work.
So E-test is proving the core technology. But what about the location itself, this Euregio-Rhine region? Why there?
It's all about the geology. They need very specific, stable, hard rock, deep underground that's well isolated from surface activity.
You need to find quiet rock.
You do. And so part of the E-test project isn't just physics. It's a massive geological survey. They're drilling deep boreholes, lowering sensors, and creating a 3D map of the rock layers to find the perfect spot to carve out a 30-kilometer triangle.
And it's also an economic project, right? I saw this program, ET2SME.
Einstein telescope to small and medium enterprises. Think about the supply chain for this. You need the best vacuum technology in the world. You need new kinds of cryogenic coolers. You need custom sensors that can work at 10 Kelvin. You can't just order this stuff from a catalog.
You had to invent it first.
And that's the idea. They're actively trying to spin up an entire high-tech ecosystem in that region to create a sort of gravity valley where local companies learn how to build the components for ET and then become the world leaders in that technology.
So this is a decades-long, multi-billion euro bet on the future of physics, which brings us to the big question, why? We've heard the chirp. We know black holes merge. Why do we need to spend all this time and money to hear more?
Because right now, cosmology is in the middle of a crisis. Some people call it a polite academic civil war.
A civil war.
It's called the Hubble tension.
And this is all about how fast the universe is expanding.
Precisely. We know the universe is expanding. The rate of that expansion is a number called the Hubble constant. The problem is we have two extremely precise ways of measuring it, and they give us two different answers.
Okay.
Method one is to look at the very early universe. We look at the cosmic microwave background, the afterglow of the Big Bang, and use our best model of physics to predict what the expansion rate should be today. And that method gives us a number, 67.
67. Got it.
Method two is to look at the nearby late universe. We look at things like supernovae and other galaxies and measure how fast they're moving away from us right now. And that method gives us a different number, 73.
67 and 73. They're not close.
They are not close, and the measurement uncertainties are now so small that they don't overlap at all. It's a 5 sigma discrepancy, which in physics means it's not a fluke. One team says 67, the other says 73, and both are completely confident in their data.
So either somebody's measurement is fundamentally wrong.
Or our entire model of cosmology is wrong. Maybe dark energy has changed over time. Maybe there's some new physics we don't know about. Something has to give.
So how does the Einstein telescope come in and play the hero?
It acts as the independent, unimpeachable referee. Because gravitational waves from merging neutron stars are what we call standard sirens.
Standard sirens, like an ambulance.
Exactly like an ambulance. If you hear a siren, you can tell if it's close or far based on how loud it is, right? But to do that, you have to know how loud the siren is supposed to be at the source.
Right. A bicycle horn might be quiet, but right next to me.
Exactly. With supernovae, the standard candles we use now, there are always uncertainties. How much dust is in the way? Was it a weird type of supernova? But with a gravitational wave signal, Einstein's theory tells us exactly how powerful the event was. We know precisely how loud the siren was at its source.
So by measuring how loud the chirp is when it gets here, we can calculate the distance perfectly.
With no fudge factors. It's pure geometry. Then, if we can see the light from the host galaxy and measure its redshift, its speed, we have distance and speed. And that gives you the Hubble constant.
So we can finally settle the argument.
We can settle the biggest debate in modern cosmology. But it gets even better. What if we don't see any light? What if it's two black holes merging in a dark, empty part of space?
Then you don't have the redshift.
No, but you can use statistics. We call them dark sirens. We detect a merger. Our detector network tells us it came from that small patch of sky. We then look at a galaxy map and see there are, say, 100 possible host galaxies in that patch.
It could be any one of them.
It could, but if you do that 1,000 times, and you cross-correlate all those possible locations with a deep galaxy catalog, the true value of the Hubble constant starts to emerge from the statistics.
Yeah.
You can measure the expansion of the universe by listening to the darkness.
That's incredible.
And that's not even the ultimate prize. The Holy Grail is detecting the stochastic background.
The background hum of the universe.
Right. Think of being in a packed football stadium. You can hear a specific person shout next to you. That's like a single black hole merger. A discrete event. But if you just listen to the whole stadium, what do you hear?
Just a roar, the buzz of tens of thousands of people.
That's the stochastic background. It's the combined gravitational wave hum of every unresolved merger happening everywhere in the universe. But buried underneath that might be something even more profound, the hum from the Big Bang itself.
You can hear the Big Bang. I thought light couldn't escape from the first 380,000 years.
Light couldn't. The universe was an opaque plasma, but gravity passes through everything completely unimpeded. So if the theory of inflation is correct, if the universe went through a period of violent exponential expansion in the first trillionth of a second,
It would have created massive gravitational waves.
a storm of them, and those primordial waves should still be echoing through the cosmos today, stretched out to very low frequencies.
And ET might just be quiet enough to hear that echo.
It is our best shot. We could, potentially, be listening to the sound of the universe when it was a fraction of a second old, probing physics at energy scales we could never dream of reaching on Earth.
We'd be doing archaeology on the moment of creation itself.
That's the goal. And along the way, we're putting Einstein's own theory to the ultimate test. Is the speed of gravity exactly the speed of light? Are there strange types of wave polarizations that general relativity doesn't predict?
And if we find something like that,
then the whole theory is incomplete, and some grad student somewhere wins a Nobel Prize for coming up with whatever comes next.
it's the ultimate stress test for our model of reality.
It is. And it's just amazing to think that it all starts here, with a 100-kilogram piece of silicon hanging in a cold, dark box somewhere under the Belgian-Netherlands border.
Puts it all in perspective. All this work to fight traffic noise and bouncy mirror wires, and the goal is to listen to the birth of time.
That's science. You have to sweep the floor perfectly before you can see the stars.
I feel like I've just been on a mental marathon trying to get my head around all of this, but it's that good kind of exhaustion, the feeling that the universe we know is about to get a whole lot bigger.
And a whole lot louder.
I won't forget that. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.